Okay, so today I will do the chapter 8, characterization of a complete Rn. Okay, so here, chapter 8, we just concentrate on a complete affine N, and so the main result is the one characterizing the complete affine N. Um, and first we show that pre-Horace-Becker ends are the Horace-Becker and the so then in 814 we show that actually complete affine N has a is in two classes. So one is this cos Horace-Becker one, and the other one is has two norms of eigenvalues, and then I show that it is actually a quasi-join. Okay. Okay. So again, we start with some strongly tame orbifold, and E is RPN, and the middle eigenvalue condition is given is that. So we again recall the eigenvalue with the multiplicity given here, and the multiplicity of norm is the number of times the norm occurs in this tuple. So we list for every eigenvalue these values, and so the weak middle eigenvalue condition is so whenever this is a largest norm, then it has to have a multiplicity at least bigger than 2. So that means that there's something associated with it, which is not in the direction of the VE. Okay, so those are the weak eigenvalue condition. And we record the parabolic group of isometric or hyperbolic plane for say I plus 1 dimensional Klein. So fixing a point. So in this SO to 1 situation, the parabolic groups are just going to be sort of hyperbolic ones. I mean these cusp groups. Okay, and so of course the terminology is conflicting with general Lie group theory because you'll have to add a hyperbolic element to get the full parabolic group. But anyway, so in hyperbolic space, this cusp group is called the parabolic group. So we have this zero-dimensional ellipsoid containing B in the subspace of dimension I plus 0. So this is in the boundary of, so ellipsoid is a codimensional one. So there's some point in the subspace. And ought P be the group of projective automorphisms. So we denote by this group acting on P, and so we restricted this to P, then you get a homomorphism. So I zero-dimensional partial cos group subgroup is one mapping on the RP2 cos group of this acting on E minus B, fixing B. So P is really so P is a subspace, and it has to act on this ellipsoid. Okay, so then this is so the cusp group is the one. So so I should say that this ellipsoid is contained in some hyperbolic space, and then this cusp group is the cusp group that is in this ought B. Okay, and so we have this O tilde in RPN, then the P plus prime denote the subgrace of dimension I0 plus 1, ellipsoid containing B. Then we denote by the subgroup. So this is just for the projective case of PGR acting on P prime, and then this restricted to, this is a restriction map. So I zero-dimensional partial cusp group is one that goes to cusp group in here. So when I0 is n minus 1, then we of course drop the partial from the partial cusp group because it's full group. So So we can also do that. The I zero dimensional cost group is you can just do any finite extension of such groups. So that's fine. To be the pressure cost group. Okay. And now we so here so we want to classify the complete affine end and so whenever you have a horospherical Rn Pn, then the Pn group acts on Pn neighborhood, and gamma P is a subgroup of the n plus one dimensional cost group. So um, maybe I should have to include some finite extension of that. Okay. So we define the intersection of these. So we have some Pn neighborhood, but now we want these to be invariant under this cost group. So we take the intersection of all these, and this is still a non-empty set because these are co-compact here. So there's a co-compact subgroup in the cost group. So we can show that this is not empty by this lemma and. Actually, horospherical ends are pre-horospherical. So pre-horospherical we mean that every direction is in the half space meets. So it is something that we defined earlier. So there's some ball, and then inside the T orb with the boundary, only the vertex is removed, and that's the end neighborhood. That forms end neighborhood. Then it's called pre-horospherical. So, but also the pre-horospherical ones has to be horospherical by. So we'll prove that. Okay. So the 8.11 is that the E is Rn and it's a pre-horospherical if it's horospherical. So that's what we want to prove. So 8.12 is one of the main results. So here E tilde is a complete affine Rn if it is either horospherical Pn or NP NC and with the fiber of dimension -2 when the virtually abelian fundamental group. But you have to change the end vertex. So originally it has some other vertex, but if you change to the proper Pn vertex, then it becomes NPNC. So otherwise it's complete to begin with. So also if it satisfies the weak middle eigenvalue condition, that only case is the horospherical. Okay. So that's what we are going to prove here. So 8.14 is the forward direction, and the corollary A15 will imply the second case. Okay. And so 8.14 is this. So this shows that in our situation there's a complete affine can has these two type of choices here. And 8.15 is that if once you change the vertex, then you get a NPNCN. Okay. So that's the two things we do. Okay, so now we prove only here we will do that later. So we prove the converse. So you have a horospherical and is of course P horospherical. So 8.13 here we will show that the equivalent pre-horospherical and the pre-equivalent. And the given NPNC and with the fibers, maybe I forgot R here, so PR NPNC. So this should be switched somehow. And with the dimension like this, so this is projectively isomorphic to affine half space. then I go to verify that if I switch back the vertex to the original one, then I can get the complete affine, complete RPN. Okay, so this involves understanding the result in this the result of this in subset 7. Okay, so we look at this K double prime is 0-dimensional, and we have act on this K double prime for B, and so then there is a foliation by complete affine and of this end orbifold by affine space, and what we need to do is, so we when we change the vertex, then this really becomes a complete affine end. Okay, so that involves so knowing that there's some ellipsoid acting on these some spaces, and these ellipsoid are translated by the uniform positive translation condition and so on. So you get the complete affine end using this. Okay, so that's the converse. So mainly we want to show the forward direction. Okay, so and we want to do the horosphere theorem. So here, so if you have a pre-horosphere, then and then the subspace of direction of lines or segment B2 boundary or to forms a complete affine space, and norms are all has to be 1, and so it's conjugate to abelian parabolic or cos group of this SON1 or PON1. Okay, and this is cos shaped, and for any compact set or contains a horospherical neighborhood disjoint from it. Okay, so the basic proof is that so first of all, we want to consider what happens with this sigma tilde, whether this is a complete affine space or not. Okay, so that's first we want to do. So suppose it's properly convex, or maybe it is some complete affine, fully by complete affine spaces, or is complete affine case. So in the first, so we show that these two cases cannot occur. So only case is complete affine. So suppose we do the second case only, then so it will act on some properly convex set of dimension bigger than or equal to 1, and so that means that G has a norm of eigenvalue larger than 1, less than 1, because of the the action is actually co-compact. So by this proposition, there is some eigenvalue like this, and so we obtain some eigenvalue different from 1. So then G is positive by proximal, and then lambda 1 is, say, the greatest norm, and the lambda 2 the second greatest norm of the G. Then we have also like eigenvalue at lambda V. Okay, so there are 3 possibility like this. So in all cases, so at least one largest normal small eigenvalue is different from lambda V. Okay, so you have lambda V, then there's something different from it. Okay, of course they could or be equal, but all right. So I assume this is this case, so we have some eigenvalue bigger than 1. So there's some different from this case, and so then so you take the generic point in U, then G and X limits to some point G infinity distincted from BE because of this case, because this is different from some eigenvalue is different from lambda B. Okay, so of course you need to change so lambda 2 is the smallest eigenvalue. Sorry. So you can also go to positive direction or negative direction, and then because they are different, then you can obtain some point which is different from the thing. But the pre-Horner sphere is that it's only the vertex is removed, and then everything else is actually tilde O. But so since U is invariant, this point has to be inside U. But that's contradiction because there's the action is properly discontinuous in O, so it cannot happen in tilde O. Okay. So that's why this cannot happen. So this and then the first case is also very similar as this properly convex case. Okay. So we can assume that this is complete affine, and then we can obtain the suppose we test normal eigenvalue different from one, then we can again apply the second and third paragraph like this. So every norm has to be one. Okay. So and this is a complete affine space, complete affine orbifold with eigenvalue equal to one only. Okay, so you can think of these as affine space now because it's complete affine, and then the restriction also has a trans matrices or eigenvalues of one. Okay, so this is a affine transformation group with eigenvalue only one. So this means that it's actually virtually nilpotent. And so you can find the torsion-free subgroup. You can always consider these as a subgroup of linear group anyways by lifting. Okay, so then you use this 7.21 of Marquis. Okay, then this is actually a cost group. Okay, so we have this. So if it's so there's some theory behind these kind of cases. And so then it's conjugate to elements in S also too. Okay. So that's how we working here. And of course, these horse pair has a Euclidean metric invariant of the group, so it's virtually abelian by the Bieber-Bach theorem, and okay, so this is just to show that gamma tilde actually acts on this ellipsoid. Okay, so that's okay, and then finally we go to forward direction of 8.12, 1.2. So here we have this complete affine case, and we have two possibilities. So gamma is virtually unipotent, or the eigenvalues are equal to one. Norms of eigenvalues are equal to one. Or it's virtually abelian, where it has only two eigenvalues and has at least one has two norm, and if G has two norms of eigenvalue, then multiplicity at B is one. Okay, and the X has a virtually unipotent group. So in this case, is in the first case is cos. Okay. So the proof of this is that so we can always get the torsion-free index group. And then so since it's affine, complete affine, you can identify with affine space, and you can write it in this way. And so for each gamma, we can write gamma Rn minus one as the affine, so one that corresponds to affine transformation here. So this is then L had to be the linear part as an affine transformation, and this B is the translation vector. And the relative eigenvalue is the eigenvalue of this. So this may not be the same as eigenvalue of the gamma itself. Okay. So gamma is an element here. Okay. Maybe. So if the at least one eigenvalue is one, since gamma x without fixed point. So this is a result by Milner and Sullivan that So if you have any affine transformation without a fixed point, then it has to have eigenvalue 1, because if not, then you can always solve for the fixed point. Okay. So then, so this has some maximal invariant vector space A where all the eigenvalues are 1. Okay, so for this gamma, and this is a gamma invariant affine space, a vector space. So it acts on this portion space by an affine transformation without any norms of eigenvalue equal to 1. So hence it has a fixed point. So this means that gamma m minus 1 acts on some affine space A prime parallel to A. Okay. And so let's consider a substrate H containing B corresponding to direction of A prime, and the union of segments of BE and B minus in the direction of A prime is an open hemisphere of dimension less than n. And A plus denote this space where this holds. H plus is a hemisphere, right? And this acts on A prime. So it follows that this gamma E acts on H plus, and so gamma has at most two eigenvalue, which is one of which is this, and the other is lambda plus. So gamma fixes VA and the eigenvalue vector in the span of H plus associated lambda plus gamma. So so gamma has some matrix form like this. Okay, so this is not just for H plus, for everything. So we have lambda plus L part and then lambda plus B lambda plus, and there might be something here, but this is 0 because BE is fixed, and you have this multiplication is 1. Okay, and of course, if you take the inverse, then you get this type of relations here. So then we have to look at this lambda 1, which is bigger than or equal to lambda plus, because it has an eigenvalue at least equal to 1 here. So so it has at least lambda plus eigenvalue because you have this multiplication. And so there are some possibilities. So lambda 1 gamma is bigger than lambda plus, and the lambda 1 is bigger than lambda BE, and then, or it could be equal. Another possibility is this is equal, and this is strictly bigger, and then another possibility is bigger, and then this is strictly equal to this. So under this assumption, lambda BE can be have only this many possibilities. So this is a different case than this lambda 1 is. I mean, this is biggest, so it has to be this or this. It could be equal, right? And then this is the case where they're equal, and so it could be equal, or lambda 1 is bigger than this, because lambda 1 is always the biggest one. So that's our possibilities, and so if satisfy B, then so all the eigenvalues are actually less than or equal to 1. Relative eigenvalues are less than or equal to 1. Because lambda plus is the biggest eigenvalue. So then it is either unit norm by eigenvalue. So everything is equal and unit, or you can take the gamma inverse and you get the case 1. Okay, so this. Okay, so because then there's some eigenvalue less than this, so you can, if you take the inverse, then you will get bigger than this and bigger than this one inverse. So if you have consider the case A, then there's some subspace where the eigenvalues like this, and then again you choose some so P-n neighborhood, and then so you choose some generic point in these components here. and then you can and then you can show the proper convexity is not satisfied. So I showed that A cannot happen in this situation. Okay. Yeah. So because it's complete affine, so every direction is realized. So affine half space is realized. So then A cannot happen. So it's either A or B, or and then we consider C or D, and then the uh, okay. So I forgot the argument really that much. But anyway, so here we satisfy C, then I can show that all the eigenvalues are actually between these two. So because if not, you can get the gamma inverse and satisfy A. And also similarly for D. Okay, so once you have that, then we send this homomorphism, and you get this sequence. R is some finite standard equal R plus, and so if you look at the kernel, then it has eigenvalue 1, and so on A, this is 1, so lambda plus A is actually going to be 1 for all n, and we are in these two cases, so therefore we have all the eigenvalues of 1, and so n is virtually nilpotent, and so now so since R is finally generated, this is nilpotent, you know this is solvable. So, and this is complete affine. So you have some solvable affine group case, then the Goldman-Hirsch showed that determinant is always 1. So if it satisfies C, then all the norm goes except so for any everything in now in here is satisfied except for this equals lambda plus, since otherwise the normal eigenvalue is less than 1 and always less than 1, and the determinant is less than 1. Okay. So similarly, you can show all the eigenvalues except 1. So you have only 2 eigenvalues. So that's what happens. Okay. And then so therefore only B, C, D will hold. Okay. So B was this case. Okay. And is unit norm eigenvalued. So the restriction to this affine case is always unit eigenvalue. So then it is actually also potent and virtually unipotent. Okay. So so that's how we do this. Okay, so now 8.15 is non-cusp case, and so please satisfy the complete affine Rn, and then it's not a cusp. Then we can choose different point, so that is quasi join RPN with fiber homology up to cells of dimension n-2, virtually a billion. So the basically we are in the case when you have only 2 norms of eigenvalues, and it is also nilpotent, so you can take the Zariski closure, which is a nilpotent Lie group, and you can also assume it's connected and so on, and so it's actually simply connected and so on. So So we can map G to Gx for the orbit is a fiber bundle. So actually, it is actually the dimension hand, and this sigma tilde has to be the same. So there is this homomorphism again. N is again the corner. Then N is also potent, and this is complete affine here, and so again, you make this G act on this space, and so on, and so it is so actually this um, right So delta G is actually going to be smooth, and so it's compact orbifold of codimension one. And also you can show it's strictly convex because it's a transitive action. And so now we look at all these space A be the hyperspace in the direction of this boundary of this complete affine space. Then this A intersect with the CLU, so this closure of the this PN neighborhood is actually properly convex at where GX, and then we can show it's actually in the interior mod G is actually compact, and this next lemma shows is properly just a segment. It can only be a segment. Okay. So now we will complete the proof later after this proof, and the 8.16 is a bit complicated, but anyway, so we show that this group X, so let's say S is the group acting on properly convex domain. It has only two norms of eigenvalue, then actually it has to be dimension 0, 1. And basically the proof is you use some Hilbert metric, and you take the corner of this group under this, and this is actually also potent again, and then we show that this orbit is actually transversal to the radial segment, because if not, it will act on the line, and then that will means that it's parabolic, so it cannot have properly convex end. So then we are in the end situation again, and then you can use the previous theory to show it cannot happen. Okay. And then also this is showing that this is compact, and this one I will skip, but it's not that hard. Okay. So once you have that the two lemma, then you know that this UA is zero-dimensional case, then it is Horo sphere because limit is only that point. If its dimension is 1, then you have segment. Then you choose a different segment. So BE is in here always, and you choose a different segment, and then you show that RQU is now a properly convex domain. I mean, it's a convex open domain, and it has only two eigenvalues, and so on. So you verify that these are also, you can consider these as a radial end, and so on. And it cannot be complete affine again from the Q because it has some multiplicity condition. So you can show that it is actually NPNCN here. Okay, and it cannot be properly convex again by the same reason. Okay, and then you replace these with the, so then you consider what happens with these. Again, these will be something of this form. So some gray sphere with the joint with some properly convex domain and so on. Okay, so then we go back to the above theory, and then show it's actually MPNCN, and so the virtual abelianness follows from the fact this SG part is 1 by 1 or 0 by 0 matrix, and then this O will act on this, and so there's some reasoning with that, and sorry, I cannot continue. So clear. Right. So then this cusp and complete affine cusp case. So if it's satisfied weak eigenvalue condition, then it is actually um, complete affine and if and only if it's a cusp end. So the reason is, of course, so horospherical end is of course complete affine. So we just need to show the forward direction, and so in the second possibility of this lemma, the norm has multiplicity 1 for non-unipotent elements and equals to the maximal norm. So this of course violates the uniform middle eigenvalue condition because at BE is always has to be the maximal one, but only the multiplicity changes. So okay, so this cannot happen, right? So another thing is next thing that I am going to do is so if you have some properly convex orbifold and it's only eigenvalues or unit norm, then only no unit norms, and it's actually holospherical. Okay, so that follows from the again from this kind of theory. The so core 8.22 is some technical lemma. So if you have some NPNCN, then the VE is a vertex, then so it satisfies NS or this, then there's some element with the eigenvalue not equal to 1 at that VE. So to prove that, you just assume that everything has eigenvalue 1, and then actually then the weak with the eigenvalue condition will have to hold again by some geometric argument here, and then once you have this weak eigenvalue condition, then because this lambda b is 1, okay, and then right, so the transverse with eigenvalue condition satisfies, so we know it is going to be some sort of NP NCN, right? So then these cannot be joined, and again using the irreducibility. Okay, so therefore only possibilities is actually um, I mean right. So right. So then you have to consider all the possibilities and look at the matrices, and so in those cases there is no real case where everything is 1. Okay, so that's the theorem we need to prove. Yeah. I mean, we need to go there and then see that there is no case where these are all equal to 1. Okay. Right. Right. Of course. Right. Sorry. I do need to. I don't really have so when it's strongly irreducible, that's true. But if it's reducible, then virtually reducible, then you have to do some more work. The